The refrigeration cycle is the reason you can survive a July afternoon in Phoenix without a block of ice and a sawdust pile. Yet most people whose names are on senior engineer business cards couldn't explain why a refrigerant boils at the temperature it does if you cornered them in a mechanical room. It is the most elegant application of thermodynamics in the built environment, and the transition from harvesting natural ice to mechanical vapor compression is arguably more important to human survival than the invention of the airplane. We have to start with the history because it anchors the physics in a way that makes the components feel like more than just expensive pieces of metal. Until the mid-19th century, if you wanted something cold in the summer, you were participating in the American ice trade, a massive industry built by people like Frederick Tudor, the so-called Ice King. He figured out how to cut blocks from frozen New England lakes, pack them in sawdust, and ship them to places as far as Calcutta. By the 1850s, people in Charleston were paying luxury prices for winter ice from Boston. This was the only way cooling happened until Jacob Perkins built the first practical vapor compression machine in 1834. The engineering he and others like James Harrison and Carl Linday pioneered didn't just give us cold beer or air conditioning. It completely redrew the map of the United States. The Sun Belt boom, the massive migration to Florida, Arizona, and Texas, only happened because air conditioning made those climates habitable for people who weren't born there. This isn't just a trade, it's an applied science that changed where humans can live and what they can eat. When you walk into a data center today, you are seeing a machine that rejects 1.5% of all global electricity as low-grade heat through the refrigeration cycle. Without it, the internet doesn't scale. Surgery isn't survivable at modern rates because anesthetic gases need cold storage, and computer chips can't be made because lithography requires temperature control to within tenths of a degree. So, when we talk about the compressor, the condenser, the metering device, and the evaporator, we aren't just talking about a machine. We're talking about a load-bearing pillar of modern civilization. Most technicians learn to hit numbers, superheat, subcooling, charge weight, without actually seeing the cycle as a single unified machine moving heat from where you don't want it to where you don't care about it. My goal is to get you to the moment where the cycle clicks. Once it clicks, you can never unsee it. Every air conditioner, from a window unit to a 1,000-ton centrifugal chiller, is the same machine, just tuned for different fluids and scales. To understand how that machine works, we have to be absolutely precise about the difference between heat and temperature. I've seen 20-year veterans get this wrong. Heat is energy in transit. It is not a substance. It is energy moving because of a temperature difference. Temperature is just a measure of how fast the molecules are jiggling. The bridge between them is specific heat. Water takes 1 BTU to raise 1 pound by 1 degree. Air takes much less, about 0.24. But the secret weapon of the refrigeration cycle isn't sensible heat, the heat you feel on a thermometer. It's latent heat. Think about boiling water. You heat it to 212, and then you keep adding energy, but the temperature doesn't move. You are adding 970 BTUs per pound just to turn that water into steam at the same temperature. That phase change absorbs more than 6 times as much energy as all the heating from 60 degrees to 212 combined. The refrigeration cycle is a latent heat machine. We choose a refrigerant specifically because it boils and condenses at the temperatures we care about, allowing us to move massive amounts of energy without having to wildly swing the temperature of the fluid itself. We pick up heat at the evaporator by boiling liquid into vapor, and we drop it off at the condenser by squeezing vapor back into liquid. Then we have the unit of capacity, the ton. It's a curious holdover from the ice harvesting days. 1 ton of refrigeration is exactly 12,000 BTUs per hour. Why? Because if you have 2,000 pounds of ice, 1 ton, and it melts over 24 hours, it absorbs 288,000 BTUs. Divide that by 24 hours and you get 12,000. Every time you say a unit is a 3-ton system, you are literally comparing it to the cooling power of 3 tons of melting ice. We also need to be clear about pressure. In this field, we talk about SINQI, gauge pressure, but physics requires CIA, or absolute pressure. Atmospheric pressure is about 14.7 psi. If your gauge says 0, the absolute pressure is 14.7. If you don't make that conversion in your head when looking at gas laws, the math fails. Pressure is our mechanical lever. By manipulating the pressure, we change the boiling point of the refrigerant. That is the entire game. Now, let's look at the 4 components in a closed loop. First, the compressor. It's the heart. It's the only part that consumes work. It takes low pressure, low temperature vapor and squeezes it. When you squeeze a vapor, its pressure goes up and its temperature goes up. It leaves the compressor as a high pressure, high temperature vapor. From there, it goes to the condenser. The condenser is just a heat exchanger, usually a coil with fins. It's exposed to something cooler than the refrigerant, like outdoor air. Because the refrigerant is hotter than the air, heat flows out of the refrigerant. It desuperheats. It condenses into a liquid, and then it subcools. It leaves the condenser as a high-pressure liquid. Next is the metering device. This is the part people respect the least because it's small and doesn't move, but it's the brain. It's a restriction. It could be a tiny tube or a complex valve. As the high-pressure liquid hits this restriction, the pressure drops suddenly. When the pressure drops, a little bit of the liquid flashes to vapor, and that process of flashing sucks energy out of the remaining liquid, making it very cold. Finally, that cold mixture of liquid and vapor enters the evaporator. This is the useful end. It's another heat exchanger, but this time, the refrigerant is colder than the air in the room. It absorbs heat, the liquid boils off into vapor, and then it superheats slightly before heading back to the compressor to start over. This is the first law of thermodynamics in action. Energy is conserved. The heat you pick up in the house, plus the work the compressor does, must equal the heat you dump outside. If you're moving 36,000 BTUs of heat from the house, and the compressor is using 12,000 BTUs of energy, that condenser has to be dumping 48,000 BTUs. If it isn't, something is wrong. The second law is the one that says heat doesn't flow uphill for free. You want to move heat from a 70-degree room to a 95-degree outdoors, you have to pay the compressor to make it happen. To visualize all of this, engineers use the pH diagram, pressure versus enthalpy. If you can't read this chart, you're flying blind. It has this saturation dome that looks like an upside-down U. Inside the dome, the refrigerant is a mix of liquid and vapor. To the left, it's subcooled liquid. To the right, it's superheated vapor. The cycle traces a quadrilateral on this chart. The horizontal top line is the condenser. The horizontal bottom line is the evaporator. The vertical-ish line on the right is the compressor, and the truly vertical line on the left is the expansion through the metering device. The width of that bottom line tells you exactly how much cooling you're getting per pound of refrigerant. The vertical height tells you the pressure ratio. This is the most important diagnostic number in the field. Pressure ratio is absolute discharge divided by absolute suction. For R410A, a typical ratio is about 2.7. As that ratio goes up, say because the condenser is dirty or the outdoor air is 110 degrees, the compressor has to work much harder to move the same amount of refrigerant. The volumetric efficiency drops. This is why AC units struggle on hot days. It's not just that the air is hotter, it's that the physics of the cycle becomes less efficient. The compression line leans further to the right, meaning more energy is wasted as heat rather than used for pressure. If you can walk up to a machine and see that the pressure ratio is high, you already know the COP, the coefficient of performance, is tanking. You're paying for more electricity to get less cooling. This is where mastery begins. Seeing the quadrilateral on the P chart in your mind's eye while you look at the gauges. You can see the refrigerating effect shrinking as the liquid line gets warmer. You can see the compression work growing as the head pressure rises. It makes the invisible visible. Let's talk about the hardware that actually does the squeezing. For over a century, the reciprocating compressor was king. It's just a piston in a cylinder. It's robust, it's well understood, but it has a weakness: clearance volume. When the piston reaches the top of its stroke, there's always a tiny bit of high-pressure gas left in the dead space around the valves. As the piston moves down, that gas expands before the suction valve can open. At high-pressure ratios, that expanding gas takes up most of the cylinder, and the amount of fresh refrigerant you can pull in drops off a cliff. This is why we moved to scrolls for residential and light commercial work. A scroll compressor has no valves and no clearance volume. It uses two interlocking spirals, one fixed, one orbiting, to form pockets that get smaller as they move toward the center. It's smooth, quiet, and more efficient. In the last 20 years, the variable speed inverter scroll has changed everything. Instead of just being on or off, it can slow down to 25% capacity, matching the heat load of the house perfectly. This is the secret to high SEER ratings. At large scales, think hospitals or skyscrapers, we use screws and centrifugals. A screw compressor uses meshing rotors, like two gears with twisted teeth. Above 1,000 tons, we use centrifugal compressors. They aren't positive displacement. They use an impeller spinning at 30,000 RPM to accelerate the gas. The biggest danger for a centrifugal is surge. If the pressure ratio gets too high and the flow too low, the gas momentarily flows backward through the impeller with a violent bang. It'll tear a machine apart. Modern centrifugals now use magnetic bearings. There's no oil, no friction, just a rotor floating in a magnetic field. It's the pinnacle of the technology. But even those machines are still just following the same four-component cycle Jacob Perkins sketched out in the 1830s. No matter the scale, the compressor's life depends on one thing: lubrication. Except for those magnetic bearing units, every compressor needs oil to survive. Oil management is the least glamorous part of the job, but it kills more compressors than almost anything else. In a hermetic system, the oil isn't sitting in a separate tank. It's mixed with the refrigerant. It travels through the whole system. If you don't design your piping correctly, that oil will get trapped in the bottom of the evaporator or in a low spot in the suction line. If the oil doesn't come back, the compressor sump runs dry and the bearings seize. This is why we slope suction lines toward the compressor and why we care so much about gas velocity. If the velocity in a vertical suction riser is too low, the oil won't be entrained. It'll just run down the walls like molasses. You need at least 1,000 feet per minute of velocity to carry that oil uphill. This is a nightmare for variable speed systems. When the compressor slows down, the velocity drops. We have to use double risers or specialized controls to make sure the oil doesn't get stranded. And the oil must match the refrigerant. For decades, we used mineral oil with R22, but mineral oil doesn't mix with modern HFC refrigerants like R410A. We had to switch to POE, polyester, oils. The problem is that POE oil is hygroscopic. It loves water. It will pull moisture right out of the air. If you leave a bottle of POE oil open on a humid day for 20 minutes, it's ruined. That moisture reacts with the oil to form acid, which eats the motor windings and causes a burnout. This is why we pull a deep vacuum, down to 500 microns, on every system. We aren't just pulling out air, we're boiling out every molecule of water so the oil stays clean. If you see a sight glass showing yellow, you have moisture, and you are on a countdown to a catastrophic compressor failure. You have to be a cleanliness fanatic with oil. It's the difference between a system that lasts 30 years and one that dies in 3. Once the refrigerant leaves the compressor, it heads to the condenser to dump its heat. The air-cooled condenser is the standard, but it's at the mercy of the weather. As the outdoor air gets hotter, the condensing temperature has to rise to maintain a temperature difference so heat can flow. This is condenser approach. Typically, we want the refrigerant to be about 20 degrees hotter than the air. If it's 95 outside, we're condensing at 115. But if the coil is dirty, covered in cottonwood seeds or dust, the heat transfer fails. The condensing temperature spikes. I've seen head pressures so high, they trip the safety switch just because of a thin layer of sweater fuzz on the fins. Cleaning a condenser is the highest leverage maintenance task you can do. For larger buildings, we use water-cooled condensers and cooling towers. Water is much better at carrying heat than air. By evaporating a little bit of water in a cooling tower, we can get the condenser water down near the wet bulb temperature, which is often 10 or 15 degrees lower than the dry bulb air temperature. This allows the chiller to condense at maybe 95 degrees, even on a 100-degree day. The efficiency gain is massive, but you pay for it in complexity. You have to treat the water to prevent Legionella and scale. If you don't manage the water chemistry, the tubes in the condenser will foul with mineral deposits. A layer of scale as thin as a piece of paper can drop the chiller's efficiency by 30%. Whether it's air-cooled or water-cooled, the goal is subcooling. This is the temperature of the liquid below its boiling point. If you're condensing at 110 and the liquid leaving is at 100, you have 10 degrees of subcooling. This is your insurance policy. It guarantees that the liquid line is full of liquid, not bubbles. If you have flash gas, bubbles, in the liquid line, the metering device can't work. It's like trying to drink through a straw with a hole in it. Subcooling also adds capacity. Every degree of subcooling increases the net refrigerating effect because less refrigerant has to flash to vapor just to cool itself down when it hits the evaporator. After the condenser, we hit the metering device. The simplest is the capillary tube, just a long, skinny copper pipe. It's cheap and reliable, but it's dumb. It can't adjust to load. It's only efficient at one specific condition. Then there's the fixed orifice piston, common in older residential units. It's a brass plug with a tiny hole. Like the cap tube, it's fixed. If the house gets hot, it can't feed more refrigerant. As efficiency standards rose, we moved to the TAX-V, the thermostatic expansion valve. It's a mechanical feedback loop. A sensing bulb on the suction line feels the temperature. If the gas is too warm, meaning the evaporator is starving, the bulb expands a diaphragm and opens the valve. If the gas is too cold, meaning we're about to flood the compressor, the valve closes. The controlled variable is superheat. Superheat is the temperature of the vapor above its boiling point. If the refrigerant is boiling at 40 degrees and the suction line is at 50, you have 10 degrees of superheat. This is our safety margin. Liquid refrigerant is incompressible. If a slug of liquid hits the compressor, it's like a car engine hitting a wall of water. It'll snap a connecting rod or break a scroll wrap in a fraction of a second. The TXV's job is to keep the evaporator as full of liquid as possible for maximum cooling, but to make sure that the last drop of liquid boils off before it leaves the coil. Modern systems now use EEVs, electronic expansion valves. They use a stepper motor and a computer. They are incredibly precise. While a TXV might take a minute to react to a change, an EEV reacts in seconds. They allow us to run very low superheat, maybe 5 degrees, which makes the evaporator more efficient because more of the coil surface is wetted with liquid. This is the brain of the modern inverter system. If the compressor speeds up, the EEV opens instantly to match the flow. It's a beautiful dance between the electronic brain and the thermodynamic heart. The useful end of this whole journey is the evaporator. In a direct expansion or DX system, the refrigerant is inside the tubes and air is blown over them. As the cold liquid boils, it sucks heat out of the air. This also dehumidifies. If the coil temperature is below the dew point of the air, water condenses on the fins and drains away. This latent work is half the reason people feel comfortable in air conditioning. In large chillers, we often use flooded evaporators. It's the opposite. The refrigerant is in a big tank, and the water we want to cool flows through tubes submerged in that pool. Flooded evaporators are more efficient because you don't have a dry superheat zone taking up space, but they require much more refrigerant. The biggest enemy of the evaporator is frost. If the coil temperature drops below 32 degrees, moisture freezes. Ice is an insulator. Once a thin layer forms, it blocks airflow. The coil gets colder, more ice forms, and soon the whole thing is a solid block of ice. We have to defrost. In a freezer, we use electric heaters or hot gas, redirecting warm vapor from the compressor directly into the evaporator to melt the ice. In a heat pump, we reverse the whole cycle. For 5 minutes, the outdoor unit becomes the condenser, getting hot to melt the frost, while the indoor unit temporarily becomes the evaporator. This is why heat pumps can feel like they're blowing cold air for a few minutes in the middle of winter. It's just the defrost cycle doing its job. To diagnose any of this, you need 9 numbers: suction and discharge pressures, suction and liquid line temperatures, and the air temperatures entering and leaving both coils. From those, you calculate superheat and subcooling. If the superheat is high and the subcooling is low, you have a leak. If the subcooling is high and the superheat is high, you have a restriction, maybe a clogged filter dryer. If the head pressure is high and the subcooling is high, you're overcharged. The machine tells you its story through these numbers, but you have to be disciplined enough to take the measurements before you start turning a wrench. As we look to the future, the working fluid itself, the refrigerant, is changing again. We started with toxic ammonia and sulfur dioxide, moved to safe CFCs like R12, then realized they were eating the ozone layer. We switched to HCFCs like R22, then HFCs like R410A. Now, we're phasing out HFCs because they are powerful greenhouse gases. The new generation is HFOs, hydrofluoroolefins, and natural refrigerants like CO2 and propane. These new fluids come with a catch. Many are mildly flammable, categorized as A2L. This means the way we install and service them is changing. You need leak sensors and spark-proof fans. You have to be even more careful with brazing and evacuation. In Europe, they're moving toward transcritical CO2 systems for supermarkets. CO2 has a GWP of exactly 1, but it operates at extreme pressures, over 1,000 psi. You can't even condense it on a hot day. You just cool it as a supercritical fluid. It's a return to the high-pressure engineering of the early 1900s, but with modern controls. The refrigeration cycle is a continuous engineering tradition. From a ship full of Walden Pond ice in 1850 to a magnetic bearing chiller in 2026, the core problem is the same: how to move energy against the natural gradient. It is an intellectually substantive, vital science. If you master the cycle, you aren't just a mechanic. You are a steward of the infrastructure that keeps the modern world functioning. I want to invite you to share this episode with anyone who's ever stood in a mechanical room wondering what that whooshing sound inside the pipes actually is. There's a lot of depth here, and once you start looking for the cycle, you'll see it everywhere, from the reach-in at the corner store to the massive plants cooling our hospitals. Take the measurements, respect the physics, and never stop learning. We're all walking on roads built by the pioneers who figured out how to make ice in the summer. Let's make sure we understand the road.